Hello everyone, we will continue our lecture series on this optimal control guidance and estimation course. We have finished 6 lectures already, and we have already gave some overview of calculus of variation in scalar, scalar variables. What I am going to do here in this particular lecture is to review that briefly, what we discussed in the last class, followed by its extensions to vector, vector concepts and all that multidimensional things, which is very similar to scalars anyway. So, first thing is a summary of what we discussed in the last lecture, the calculus of variations for scalar problems especially. So, this is the concept that we discussed. We discussed something like on one side there is a function and its increment, and the other side is a functional and its increment, and both appear to be quite similar, provided the x axis turns out to be like in this particular case it is free variable time, but whereas in this it is the x of t basically. So, it is, you can interpret it something like a function of function sort of thing, that is how, where this delta x can be a variation with respect to time. Okay. Then if it varies with respect to time, then how this j varies, okay. That is ultimately the implication basically. Then we discussed many things about in increment of a function is this delta f approximated as df. Similarly, increment is delta j approximated as del j. Okay, slight notational change, this is df was it is delta j sort of thing. So, just to make sure that this is variations. Then we discussed about differential of a function and variation of a functional, things like that, and we carried out this algebra, and using this Taylor series we landed up this kind of expression for delta f, and then it turns out that when delta t goes to 0, and we will end up with something like df. Okay. So, in general you can tell df is something like f dot into delta t in general basically. So, a very similar concept you can do this way also here, and you can take first variation, second variation, things like that, where first variation is can be computed this way. And as I told last class, if somebody does not tell by default variation means first variation can be computed this way. We also gave examples how to compute and things like that in the last class actually. So, then coming to the boundary condition, we discussed two classes of boundary condition, and the fixed endpoint problems and free endpoint problems. Fixed endpoint problem can be kind of fixed both in time and state, or time in the free variable. This time is the free variable and x is the dependent variable. It can be fixed both sense. T0 at T0 x can be fixed, at Tf x can also be fixed, or it can also be something like free endpoint problems, where the endpoint can be completely free, or it can be required to lie on a specific curve. And I gave you an example of satellite launch and all that. When you launch a satellite, does not matter where you join the orbit, but from there onwards it will keep on staying in the orbit anyway. So, all that it matters is just to leave it somewhere in the orbit on orbital conditions actually. So, that is how these problems are defined that way. Alright, so then optimum of a functional we also discussed, and we had this formal definition that a functional is said to have a relative optimum at x star of t. Remember, it is not a particular point, but x star itself is a function of time. So, it is a functional is said to have a relative optimum at x star of t if there exists some epsilon which is greater than 0, such that the function this x of t will satisfy this kind of a condition. Okay. Whenever it satisfies this, then you have this increment of j should have the same sign. That means, if you are talking about a minimum, then this delta j of x minus j of x star should always be positive, no matter what kind of variation you talk about. If whatever variation you have, okay, either up or down or whatever it is actually, okay, irrespective of whatever variation you have, delta j will keep on getting positive. That means, j of x star is supposed to have a local minimum. And similarly, if delta j is less than 0, then j of x star is supposed to have a local maximum actually. Okay. And obviously, if the relationships are satisfied arbitrarily large value for it is satisfied for arbitrarily large value of epsilon, then j of x star is said to have a global optimum actually. And we also discussed about this variation concept and all. If x star happens to be an optimum path, then all that you are talking about is a neighborhood path of that actually. So, whatever neighbors you are getting, that kind of a thing we are talking about actually. Okay. So, then we discussed about some fundamental theorem of calculus of variation, and it turns out that for x star of t to be a candidate optimum, the following condition has to hold good. That means, the first variation has to be 0, for all admissible delta x. See, this delta x turns out to be the difference between these two actually. So, for all admissible delta x, your delta j has to be equal to 0, that happens to be a necessary condition, and a sufficiency condition happens to be second variation should be greater than 0 for a minimum, or second variation should be less than 0 for a maximum. And when it I mean this concept are kind of you can think about very parallel to the static optimization, but they are ideas of calculus of variations rather. We also discussed this nice beautiful little fundamental lemma, okay, and it was told that if for every continuous function g of t this equation is satisfied, this integral equation is satisfied, okay, where the variation delta x is continuous in t, okay, then the the only condition that is required is delta x has to be continuous, that is all. Okay. Then it turns out that g of t has to be 0 in the entire interval. Okay. So, that is that is a nice property, and then many times we will use it also actually. Okay. And this was a very simple proof also. We took at the interval, and then in that interval we took the function everywhere 0, but in that interval it is not 0, and we can always construct a delta x which is again non-zero in that particular interval, and then this integral happens to be non-zero. Okay. If you do that, then this account that is a kind of counter argument sort of thing. So, taking help of that we could show that it cannot happen. So, with that proof by contradiction and all that. So, then we landed up with the conclusion that g of t has to be 0. It looks a very simple theorem, but there is a lot of great implications later. Then about conditions of optimality, we defined the problem that we have to optimize this kind of a function, okay, where t0 and tf both are fixed, and all that you have to do is to make sure that the first variation is 0. And after some algebra using this partial fraction of partial fraction of this integral and all that, we could able to show that it ultimately leads to these two conditions. When the first condition is called EL equation or Euler-Lagrange equation, okay, and the second one is transversality condition, which leads to this boundary condition sort of thing. And we also noted that part of this equation might be already satisfied by problem formulation. In other words, if your x 0 is fixed, it is not free, then the dx naught is already 0. So, this condition is already satisfied actually. So, whatever is not satisfied, you can extract from there. Whatever is satisfied is already satisfied anyway. Okay. So, remember this equation is valid for the entire path from t naught to tf, whereas these conditions are valid for t0 and tf only basically. Okay. So, this is a differential equation for this will give a corresponding differential equation, and this will give a corresponding boundary condition sort of thing. So, using these two we are supposed to solve the optimal dynamic optimization problem basically. So, now this quickly this proof that followed is something like this. It has this delta L, we took it, and delta L is by definition like this, and we expanded using Taylor series. Okay, this is the first term in derivative and then higher order terms, and then if you take in the limit, delta L will become delta L, this delta L, and then that turns out to be like that. So, this delta J can be approximated something like this. Okay. And then this particular part, this second part of the integral, you can kind of integrate by parts. Okay. Okay. So, then do this algebra, and then end up with this kind of a conclusion. This part being like that, and then you can put it back here, and then ultimately it leads to that. So, okay. So, if this has to be 0, then this has to be 0 and that has to be 0, and that is how we got these two conditions of optimality that I just talked actually. Okay. So, the same trick will hold good for vector algebra also, that is why I thought of kind of revising it again. So, this ultimately leads to these two conditions, and condition 1 must be satisfied regardless of the boundary condition or end condition, but second part of the equation, that means this equation may already be satisfied by the problem specification. Okay. So, the amount of extra information contained by this equation varies with the boundary condition specified actually. So, that means depending on the specified boundary condition, you have to extract additional information from this condition. In general, this was in a restrictive sense, we tried to expand that, and then in general we ended up with this kind of thing, I mean this general transversality condition sort of thing, when t this variation of t was also allowed. In other words, variation of the initial time and final time, that was allowed actually. Okay, where you start, where you stop is up to the designer also in a way. So, sometimes the problem when you start and when you stop, okay, that can be free also in a way. So, if you bring that into account, then this leads to something like this, and then we discussed about various special cases, case 1, case 2, I think up to case 5 under some different conditions. That means, if both the endpoint are fixed, that means both time and x naught at t0 and tf are all fixed, then this does not obviously give any additional information, because every delta x0, delta xf, delta t naught, delta tf, everything goes to 0. But if t naught and tf are fixed, but x naught and xf are not fixed, then obviously this part goes to 0, delta tf and delta t naught both are 0. So, we will end up with only this part of the equation. Similarly, if t naught and x naught are fixed, okay, that means tf and xf both are free, then you can consider only the tf part of the equation, and then you will end up with something like this. Okay. And similarly, if depending on what is fixed and what is free, we kind of take the other part into account, because whatever is given, if it satisfies some part of the equation automatically, we consider that as I mean as taken sort of thing. Okay. So, this is how we extract this information content from transversality condition. Okay. Ultimately, the key idea here is the number of differential equations and number of end conditions should be same. Okay. And then it depends on how many free variables are there with us and how many extra information can be derived from this equation actually. So, depending on an example and all, we will talk later, it will be more and more clear how to use it actually. Okay, so the very special case at the end, when t naught and x naught is fixed and tf and xf are constrained to lie on a given curve, then you have to go back to that, because it is fixed anyway. So, this t naught x naught does not give any extra information, but tf xf we cannot take that as 0, okay, this part of it, delta xf and delta tf cannot be 0, but they are supposed to satisfy certain constraint equation. Okay. So, this constraint equation can be derived something like this, okay, because xf is a function of eta ta. Okay. So, from that delta xf is nothing but that. So, we can substitute that and then end up with this, and where delta tf is not really 0, because this is constrained to lie on a given curve, that means your final time is kind of free actually. Okay. So, if that is not 0, the coefficient has to be 0, and that is how we will end up with this additional equation, okay, which is needed for this kind of a problem definition actually. Then we also discussed a little bit on second variation. On the second variation, we expanded the second term of the Taylor series, and then observe that this lends up, this gives us this Hessian matrix sort of ideas, and then we define this pi, weak pi, okay, that matrix evaluated at the optimum point, and if it happens to be a PDF matrix, then it is a minimum, and if it happens to be a negative definite matrix, it happens to be maximum actually. Okay. So, first what you have to do in a given problem is to evaluate this matrix pi first, and then evaluate whether the pi is a positive definite matrix or not actually, or negative definite matrix. Okay. If neither of the above, then further math is obviously required, and like static optimization, if you remember, we have this third term, fourth term and things like that, and obviously those things are beyond the scope of this course actually. And also remember, unlike static optimization, in this particular thing, x star and x star dot both are time dependent, they are not really a specific point value. Okay. So, they are x star is a optimal solution which is a function of time, basically that is a path trajectory that you are looking for. So, this what you will evaluate here pi is not really a constant matrix, but it is a function of time. Okay. So, when you talk about whether this matrix is positive or negative, it should remain positive or negative for all time actually. Okay. So, for in the entire interval, this matrix should turns out to be a positive definite matrix. That means, one easy way of doing that is just evaluate the eigenvalues symbolically as a function of time, and then plot it in this interval actually. If they all remain positive, okay, then you are done sort of thing. Also remember, as a last comment, that this test that we are just talking about is valid only for free optimization problem. The moment you bring in some sort of a state equation constraint or any other algebraic constraint, things like that, then If the constraint is active, then obviously this condition does not hold actually. Okay. Alright, so this is what we discussed in the last class. How about extending some of these concepts for the vector problem? Okay, because that is where we are our main interest will lie, because all our state variables are typically of n dimensional control, is m dimension, things like that actually. So what I mean, consider the same problem, but in multiple dimension, and to begin with we consider the problem without any constraint actually. Okay. So, just I mean what you see here is very similar concepts. The only difference will be the small x will be replaced by capital X now, where this capital X contains n dimensions, I mean n components x1, x2 up to xn actually. Okay. And obviously again the similar sort of ideas will take T0 and Tf both are fixed, and our objective is to make sure that delta j goes to 0 for arbitrary delta x actually. Okay. So, again the similar algebra it will do that in a second, but using the similar algebra it will end up very similar looking equation. But remember these two equations now are not exactly same as what you have seen before, especially this particular equation contains n equations really, del L by del x1 minus d by dt del L by del x1 dot equal to 0, then you can substitute by x2 x3 like that. So, it really contains about n equations actually. Alright, and here transpose is also a must, because this itself is a vector and that is also a vector. So, what you are talking here is very closely what we have done in scalar problem, but not exactly one to one sort of thing. And proof also will this particular condition derivation proof will also be very close, but just be careful about your algebra, that is all actually. Okay. Because vector matrix algebra is not very similar to scalar algebra, that is the only thing actually. So, what you are looking for is delta j, okay, has to go to 0, and delta j is something like this, and obviously the second term again is a problem. So, we try to kind of simplify the second problem, and second problem this delta x dot is nothing but d by dt for delta x by definition, and now we integrate by parts, and then we just tell okay, this is the first term, this is the second term. So, we will keep that as first term into integration of the second term, which is delta x minus and differential of the first term, okay, times this one. Okay. Right. So, this is how it is. I think most perhaps this is like this. Okay, I think one term is missing there probably. Maybe this is a transpose here. Okay, so just note that transpose. I mean, there is a, because this again this is a vector matrix algebra. So, this has to be noted actually, because you just cannot afford to lose this transpose and all that actually. Okay, because if this is a vector and that is a vector, ultimately multiplication has to be a scalar actually. Okay. Alright, so this is how it is, and then we carry on with this same thing. I mean this term ended up with something like this. This leads to that. So, we take this term and substitute it back, okay, in this expression, and then see that these two terms, and then substitute that, and then end up with something like this actually. Okay. Exactly same, just that this transpose cannot be omitted, and then left cannot go to right, things like that actually. The multiplication order has to be maintained, transpose has to be in place, things like that way. Okay. So, okay. Yeah, there is one more transpose missing looks like. So, let me correct that. This is where I think probably here. Okay. Anyway, so this is how algebra proceeds. Okay. And then same thing, it goes to 0. So, obviously, this coefficient has to go to 0. So, this first term will give us the CL equation, and the second term will give us the transversality or boundary condition basically. Okay. So, in any given problem it is our duty to satisfy both the conditions and carry out the necessary algebra, which will make sure that these conditions are satisfied. And again extending the transversality condition, we can go for these similar ideas, del L by del x transpose delta x and things like that. And special case is very similar to the scalar cases, and remember these are the cases that I am talking actually. Okay. These are the cases that I am talking. That means either fixed endpoint or or partly fixed, or the T naught and T f both are fixed, or the states are free, like that actually. That kind of conditions we are talking here, and everything will be very parallel to what you have discussed there. Just that you have to be slightly careful about your algebra actually. Okay. All right. So, this is the condition that is there. Now, okay, that is all about free optimization, which is very parallel to the scalar case. Now, how about constraint optimization? That is more important, because many of our problems will invariably have an equality constraint in the form of state equation later. So, we are more interested with this constraint of variational problems, and that too with multiple dimensions. Now, how does it go? Again, it's very close to this static optimization sort of concepts here. So, what you are looking for the problem is to optimize this cost function, okay, or rather the cost functional j, okay, which can be a nonlinear function, okay, some meaningful nonlinear function containing both x dot as well as time, okay, and it is subject to this this equality constraint. And if you notice a little bit carefully, and suppose x is really the state of the problem, state vector of the problem, then this constraint is nothing but state equation sort of thing, okay, because normally we have x dot equal to, okay, normally we have something like x dot equal to f of x u sort of thing, or whatever. You can take that out for a second, okay, and then tell, okay, that is how it is. My, let us say x is, I mean u is, we are not talking right now. So, let us not talk about that. So, we talk like this. So, then I can consider that as x dot minus f of x equal to 0. Okay. So, this is nothing but my phi, what I am talking. Okay. This is phi of x and x dot. Okay. So, this all right. So, what you are talking here is some optimization of a cost functional subject to an equality constraint in the form of algebraic equation, or in the form of state equation really. It can be a function of both x and x dot actually. Okay. And remember, this dimension of this constraint need not be same as the dimension of the state. It can be very different, n and n tilde can be very different actually. Okay. But typically when you talk about a state equation, then obviously both equations are same. So, the equation n tilde and n will be same actually in most of the cases. Okay. Anyway, so coming back to this, we are interested in optimizing this cost functional subject to this equality constraint. Now, how do you do that? Okay. Then I go back to this Lagrange's existing theorem, and this existing theorem tells us that this constraint optimization problem, okay, what you are looking at. See, what it tells is that there exists this same dimensional co-state vector now, okay, lambda is a function of time again, very close to x actually, whatever meaning is that, same dimension as x rather, okay, same dimension as this constraint n tilde rather, okay. So, what it tells? It tells there exists a variable called lambda of t, okay, say of same dimension as the number of constraint, okay. So, that if you construct this j bar, okay, this way, and try to optimize it as if it is a free optimization problem, then it is equivalent to solving this problem basically. That is all it tells. Okay. So, there exists a lambda of t such that the above constraint optimization problem leads to the same solution as the following constraint cost function, on constraint cost functional. Okay. So, all that you have to do is construct this j bar, okay, and then treat as if it is a free optimization problem, but the variables are increased now. That means, you do not have only freedom in x, you also have to cater for freedom in lambda actually. So, that is kind of what is mathematically called as dualization of the problem. So, you are actually taking it to some sort of a higher dimensional problem, because lambda itself is not a constant vector, it is a time varying thing. So, you really need a differential equation for that and all. We will talk a little more on that as we go along actually, especially in the next lecture. But anyway, so the Lagrange's theorem, Lagrange's existence theorem tells us that all that you have to do is to construct a j bar like that, and then treat it as a free optimization problem in the form of in the free variables being x and lambda both actually. Okay. So, what do we do now? We define something like an L star, which is L plus lambda transpose phi, okay, and then we simply go back and tell, okay, we will apply the EL equations directly. We do not have to really keep on deriving the EL equation again and again, because we know this is a function of L star is a function of x dot t and probably lambda also. So, let me erase a mistake here. Okay. This is a function of lambda as well. Okay. Because L star contains lambda actually. Okay. Lambda is here. Okay. L star contains lambda actually. Okay. So, what you are doing here is considering that and then applying the EL equation twice sort of thing, two equations actually. First is with respect to x variable and second is with respect to lambda variable. Okay. So, because you can always define something like okay, if you are not comfortable with this idea there, you can always define some other vector, let us say some capital X, which is actually x and lambda. Okay. With first is x variable and then next is a lambda variable, and apply the EL equation with respect to the capital X. Okay. Then it is equivalent of applying it twice with x and lambda separately, because because by the definition this will be like components of big X. Components of big X will be first contain x and then second contain lambda actually. So, it is as good as applying it or writing it separately basically. And also remember this equation what you are seeing, L star does not contain any lambda dot expression. Okay. So, that because of that this partial derivative with respect to lambda dot happens to be 0. Okay. So, time derivative of that is also 0 basically. So, that is how it leads to this del L star by del lambda equal to 0 actually. Okay. How about transversality conditions? Again same thing, there are two things here, first is with respect to x and second is with respect to lambda, and again because lambda dot is not there. So, any partial derivative with respect to lambda dot is 0. Okay. So, we essentially will end up with this kind of equation. Okay. First equation is del L star by del x minus d by dt of del L star by del x dot equal to 0, and the corresponding to that what we call as co-state equation in general. So, del L star by del lambda equal to 0. Okay. And remember when you do this del L star by del lambda, okay, this L star is like this. So, del L star by del lambda is nothing but phi. So, what you are telling is phi equal to 0 and that is nothing but that. Okay. So, the constant equation appears again as a set of necessary, as a part of the necessary condition actually. So, the constant equation gets embedded into the part of the solution basically that way. Alright. So, what you are doing here is this kind of thing, first is with respect to x variable, then with respect to lambda variable. When you do this with respect to lambda variable, our constant equation reappears actually, same constant equation comes. Okay. So, this is how it is. So, what you are looking at, we are looking at a problem with some n dimension from x and n tilde dimension from constant equation, okay, and one freedom, if your TF is free, okay, then one more freedom comes from TF actually. Okay. So, essentially we have to have these boundary conditions for this n plus n tilde plus 1 sort of thing that way. Okay. So, n conditions are already there because T x naught is fixed, okay, T naught x naught that kind of fixed. And the other things can be derived from here. Okay. The transversality condition tells something like this. Okay. So, when you apply this leads to this n tilde equation sort of thing, and then you have one more condition that L star of TF in delta TF equal 0. But since TF is free, it leads to this L star TF equal to 0. Okay. So, you have these many freedoms and you also have equivalent boundary conditions sort of thing. So, you should be able to solve it actually. Okay. Okay. Alright. So, then there is another class of constraint that pops up in many of our application problems. Okay, this non-holonomic constraints and all that which they call. Okay, so that means this is what it is. Okay, this non-holonomic constraint appears in the form of state equation. There is also another class of constraint which is called isoparametric constraint. That means we are not interested in a particular value per se of this particular function. What we are interested in an integral value of that function has to be equal to some value k actually. Okay. What's an example? An example probably like what I can think of is suppose you are talking about a let us say some sort of a target entry ballistic missile guidance, let us say. So, you have to have it here and the vehicle goes there, and then there is something, somewhere there is a target there. So, that means this is the center of earth, let us say. Then what you are looking for is this angle. Okay. This angle is called something called range angle actually. Okay. So, what you are looking for is you have to guide this vehicle in this segment. Okay. This is your supposed to guidance ends at the point of burnout. Okay. You guide it in such a way that it will follow the same trajectory that you are looking for. Okay. This. Okay. It will follow the same trajectory that you are looking for, and ultimately it will end up the target. And equivalently, it tells you that okay, this angle that is getting covered, this range angle and all, at the end, okay, not in the guidance segment, not in the this T0 to Tf for our guidance purpose can be ending here, but you extend that and then tell okay, after so much of time it will finally going to fall somewhere. Okay. So, in that particular thing, I mean, by that time whatever angle I covered has to be equal to some value basically. Then only my vehicle will be reaching there, otherwise it will be somewhere else actually. Okay. So, that is not acceptable. So, that kind of problem is called something like isoparametric constraint, and you can think of many different applications as well actually. Okay. This is just a small example sort of thing. That way. Okay. So, there are cases where it will appear this kind of constraint. Now, how do we handle that? Okay. Because we have not talked about anything about that so far basically. Now, if you are a little bit clever, then you can think that okay, integral is kind of an counterpart of differentiation actually. So, then what I will do, I will define another kind of state equation, state variable sort of thing, another free variable x n plus 1, which is not part of n. Okay, remember x contains x1 to xn. So, I will define another variable x n plus 1 such that x n plus 1 dot is nothing but that. Okay. So, what I do? If I integrate it both sides from T0 to Tf, what I am learning here, because this is by definition x n plus 1 dot is nothing but that, and that is nothing but this constraint equation basically. So, this integral of this x n plus 1 dot dt is nothing but equal to k. Okay. But this one can be expanded now as x n plus 1 Tf minus x n plus 1 T0 equal to k. Okay. So, this equation that you are looking for, okay, this particular equation, okay, is actually two free variables and one equation, right. I mean, we do not know, as long as the difference is k, then we are okay, because this appears as a this non-holonomic constraint sort of thing. So, this constraint is accounted for. Only the boundary condition sense we need something, and we got it actually, but it happens to be like two free variables and one equation actually. So, what do we do now? So, essentially the idea here is you can choose one of these two and fix the other one, okay, because anyway it is a free variable sort of thing. Okay. As long as this differential equation is satisfied, then we are done anyway. The boundary condition does not matter that much as long as the difference happens to be k. So, you can select one and fix other, and whatever you are selecting can be interpreted as something like a tuning variable. That means, if you select a different value, the results may be different and all that way. So, it happens the one that you select happens to be a tuning parameter, the rest of the thing will go as part of the equation actually. Okay. So, if you are not sure what value to select and all that, obviously an idea is select the x n plus 1 T0 equal to 0, and then x n plus 1 Tf will automatically become k. Now, that is just a guideline sort of thing actually. Okay. So, again I am emphasizing that because many practical problems we may end up with some constraint like this for the objective to be met actually. So, in those situations, one idea is to define an additional free variable x n plus 1 and do this, bring in this additional constraint equation in the form of non-holonomic constraint actually. Okay. Associated boundary conditions will be derived from the constraint equation. So, what is the summary again? The summary is the following additional non-holonomic constraint is introduced, okay, with the boundary condition like this. Okay. And again this 0 can be some other thing. If you select some other number, then this k plus that number will appear here actually, and that happens to be your design flexibility sort of thing actually. Okay. So, what is essentially done is the original problem is augmented with this information, this constraint equation with this boundary condition, and then it is attempted to, you attempt to solve this actually. Okay. Let us go for a small example problem now, which will make our idea slightly more clear probably. Okay. So, this is a standard very small example problem. I will encourage everybody to solve it really using pen and paper basically. Yes, so, because these problems will get our ideas clear actually. What you are looking for? You are looking for minimizing a cost functional like this, okay, a standard cost functional, quadratic cost functional, with x1 of 0 equal to 1 and x1 of 1 equal to 0. Okay. Remember that. Okay, and there is absolutely no constraint on x2 per se. Okay. Where this equation is constrained, this x1 is further constrained by this differential equation. x1 dot is minus x1 plus x2, and x1 boundary conditions are known to us actually. Okay. But we are more interested in minimizing this cost function. So, for a second, if somebody is clever, you can think of, well, x2 of t, it can be interpreted something like control variable u of t. Okay. So, if x2 of t happens to be control variable, then this is the way the control problems do appear actually. This will be something like x square plus u square. Okay. Well, let me do that probably. Okay. This is this. Suppose I define x1 as nothing but x and x2 as something like u. So, then j, this j will be nothing but 0 to 1, 0 to 0 to 1, okay, x square plus u square into dt, okay, subject to, okay, x dot equal to minus x plus u, okay, and then boundary condition is x of 0 equal to 1 and x of 1 equal to 0. Okay. That means, in a time thing, if you talk about x, you are talking about x of 0 equal to 1. So, you have this 1 and x of t equal to 1 somewhere here, it has to be 0. I do not know how it will develop the entire trajectory. It may not be a straight line. So, it can develop whatever way it wants actually. Okay. It can develop whatever way you like to have. Only condition is it has to optimize this cost function on the way. It has to minimize this cost function actually. Okay. So, this is, if you interpret this problem, what you are looking for here, it is actually the same problem is getting embedded in the form of this x1, x2 variable here actually. Okay. So, in other words, we are trying to solve an optimal control problem here in an indirect way actually. Okay. That is the message there. And also remember this path that I put, we do not know how it will look like right now. Okay. So, we will see whatever the equation pops up, okay, accordingly it will evolve actually. Okay. But it has to satisfy the boundary condition, that is there is no compromise on that actually. Okay. So, that means x of 0 has to be 1, x of 1 has to be 0. Okay. They are the two conditions actually. And also remember, we are mainly interested in the interval 0 to 1. We are not interested in anything beyond that. These are this fixed final time problem sort of thing actually. Your initial time is fixed at 0, your final time is fixed at 1. Okay. There is no variation of those values actually, and this final initial value of the x is 1 and the final value of x1 is also 1 actually. Okay. So, that there is no freedom of that. So, you can think of it is something like a fixed endpoint condition problem actually. Okay. All right. So, let us proceed further. So, what do you do actually? We will not worry about x and u and things like that. We will confine our discussion with x1 and x2, because we have not even introduced an optimal control problem, which we will do it in next class anyway. But I mean, looking at this, we will just go back to our EL equation and try to get an answer for this actually. So, what you are doing? There are two ways of doing that. One, let us follow method 1 first. Here, I will be slightly clever. I mean, then okay, I will look at this equation and I know everything, all the algebra that is necessary in the form of x1, x1 dot and all that way. So, how about simply eliminating x2 from here? So, I will try to eliminate x2, okay, and then x2 is nothing but x1 dot plus x1, okay, and I go back and substitute that there. One part is x1, so I will x1 square, so I will keep it x1 square as x1 square, and x2 square, okay, is x2 is nothing but x1 dot plus x1. So, I will substitute that x1 dot plus x1 square. Now, it is a problem of purely in the form of x1, x2 is gone actually, and the x1 boundary conditions are also available. So, we will be able to solve it actually. Let us see how to do that. So, what is the EL equation? EL equation tells us that this is true, okay, and also I mean there is a small mistake here, this is both x1 and x1 here. Okay. All right. Okay. So, we put this del L by del x1 minus d by dt of del L by del x1 dot equal to 1, I mean equal to 0. Then what you are doing here is nothing but this del L by del x1. Okay, the L is like this. So, what is del L by del x1? 2x1 from here, and this is nothing but this I mean this chain rule of derivation to apply, then it turns out to be 2 into that, and then partial derivative of del x1 by del x1, that is 1 actually. Okay. So, 2x1 plus 2 of that minus d by dt of partial derivative with respect to x1 dot now. Now, when you do x1 dot, then this one there again the coefficient is 1. So, you will end up with that actually. Okay. So, when you do this partial derivative with respect to x1 dot, do not consider x1 as dependent on that and all that. They are two different quantities actually. Okay. So, we end up with something like this equation. So, now it is time to simplify a little bit. We simplify. Okay, it turns out to be like this, and essentially you can see that this is nothing but x1 double dot. Okay, and this guy cancel out. Okay, this x1 dot and x1 dot cancels out here, plus and minus. Okay. And I am left out with this this differential equation. Okay, x1 double dot minus 2x1 equal to 0. Okay. So, this is rather easy to solve. I mean, this is linear equation sort of thing, second order linear equation, homogeneous. So, characteristic equation turns out to be lambda square minus 2 equal to 0, and then lambda equal to plus or minus root 2. So, x1 t is nothing but c1 times this plus c2 times the other one. Okay. And x2 obviously we know, because x2 we already eliminated, this is what it is. The moment we know x1, okay, we can always construct x2 from this algebra, x1 dot plus x1. Okay, because x1 is purely a function of time now. So, I can construct x2 very easily rather. Now, what is the boundary condition? Boundary condition tells us that these two boundary conditions, x1 of 0 is 1 and x1 of 1 is 0. Okay, so, when you substitute t equal to 0, then e to the power 0 is 1 anyway. So, what it gives us? This is 1 equal to c1 times 1 plus c2 times 1. So, this is nothing but 1 equal to c1 plus c2. So, I am putting that here, 1 equal to c1, okay, plus c2. This is embedded here. The second one is at t equal to 1, okay, that means when this coefficient will become e to the power root 2 and e to the power minus root 2, okay, that is what it will come here, okay, that value will become 0. So, or if you are not comfortable, you can just write these equations again. So, this first equation leads to 1 equal to c1 plus c2, the second equation leads to 0 equal to c1 e to the power root 2 of root 2, because root 2 times 1, that is what it will turn out to be. Okay, so, this is e to the power root 2, okay, plus c2 e to the power minus root 2. Okay. So, these two equations are written in a vector matrix form here. Okay. Alright, so this is how it is, and then it is easy to compute C1 C2. C1 C2 is A inverse B sort of thing. Okay. So, compute that and you get it something like this. You can further simplify the algebra, or you can stop here, computer will evaluate whatever it is actually. What we got, what is the value of C1 and C2 basically. Okay. So, this is once you get the value of C1 C2, you are done, because x1 of t happens to be like that and x2 will happen to be like that. Okay. You are done with that actually. So, this is one way of getting that actually. Okay. But it is not a very good way of doing that, this method of elimination and all that. Okay. As for higher dimensional problems, it may not be possible actually. So, we need to have a direct way of doing it and things like that. Yeah. So, let us go to this method 2, which we just studied, that Lagrange approach sort of thing. So, remember this is the constant equation, right. This is a cost function that I want to minimize subject to this constant equation. So, we can introduce this Lagrange variable and then introduce additional equation and all that actually. That is what we are going to do here. So, L star is nothing but L plus lambda into that phi, whatever phi is actually. Okay. So, this will end up like that. Now, we have real equations in 3 variables, because x1, x2 and lambda. Okay. We have not eliminated x2. So, x2 happens to be a free variable also basically. Okay. Just that x2 dot is not there and lambda dot is also not there. So, these two quantities will go to 0. Okay. So, what you are looking for is this equation and these two equations actually. Okay. Right, this L star will contain L plus lambda transpose F or transpose phi, but it's a single equation anyway. So, we don't need the transpose, it's a scalar equation, and L is nothing but that. L is whatever comes inside the integral. Okay. So, this is how it is constructed. L is whatever comes inside the integral plus lambda times, in general it is lambda transpose times phi, but here it is one scalar equation anyway. So, you take lambda times phi, phi is nothing but that. Okay. This is by definition. Okay. Then when you start applying L equation, it is nothing but individual component wise you will apply. First we apply with respect to x1. So, del L star by del x1 minus d by dt del L star by del x1 dot equal to 0. Similarly, you replace with x2 and then formulate this equation, and that by lambda and formulate this equation. And it turns out that there is in this L star there is no x2 dot expression anywhere, and there is no lambda dot expression anywhere either actually. Okay. So, that is the reason why these two becomes 0. Okay, these two are gone. So, you will end up with this equation as well as these two equations that needs to be solved actually. Okay. So, what does it lead? What does it lead to? Del L1 del L star by del x1 minus dy dt of this quantity. Okay. So, this will lead to this one, this equation. Okay, let's and then del L star by del x2 will lead to that equation, and then this del L star by del lambda will lead to the same constant equation that you have seen before. Okay. Once you take out del lambda del L star by del lambda equal to 0, that means this is equal to 0. This x1 dot plus x1 minus x2 equal to 0. That is nothing but the constant equation that we started here. Okay. Alright, so this is how it will appear basically. Okay, this algebra sense, well, it is very simple rather. Let's try to do something actually. So, L star is like that. So, del L star by del x1. Okay. Okay, if you look at that, that is nothing but 2x1 plus lambda actually, because 2x1 from the first term and then lambda will come. Similarly, del L star by del x1 dot, if you talk about, there is nothing but lambda basically. Okay. Okay. So, what you have here is 2x1, okay, this is 2x1. Okay. So, when you substitute this equation, these two, what you will end up with 2x1 plus lambda, okay, from the first one, plus d by dt of lambda, that is lambda dot equal to 0. Okay. That is what you are getting here. Okay. The very first equation, that is 2x1 plus lambda from this side, then the lambda dot from the second one actually, that is equal to 0. Okay. Similarly, when you do this algebra of del L star by del x2, then all that you are having is here 2x2, okay, minus lambda. Okay. So, that is 2x2 minus lambda equal to 0. And similarly, when you do this other one, that is very straightforward. This equation is to be there, all the coefficient of lambda has to appear, and that nothing but the same constant equation. That is how we get it here actually. Okay. Now, it is time for us to solve these three equations, and these three equations can be solved, okay, in variety of ways obviously, and we can solve it whatever way we want actually. Okay. Let us follow one approach where you can think, okay, I can eliminate lambda from equation 1b. Okay. So, I will eliminate that, I get lambda equal to 2x2, okay, and x2 is nothing but x2 into x1, I mean x2 is nothing but x1 dot plus x1 here, this equation. Okay. So, 2 and so now you can go back and tell, okay, I will use this equation 2 and 1b, okay, gives me that kind of equation basically. Okay. All right. Lambda you have eliminated. Okay. So, what you are getting here, lambda dot is nothing but the 2x, okay. Well, I don't know, 2 into 1a probably. Yeah, I think this should be probably 1a. Okay. Just check it, I mean, you can do it yourself probably. Okay, if you use this now, what have we done here? What have we done here? We have eliminated lambda from here. So, we used this equation 1b in a way. Okay, and then when you x2, okay, then x2 we have used this equation also, right, by putting this. Okay. What you have not used is this equation actually. So, this equation is substituted back, and ultimately get lambda dot is nothing but 2x1 plus lambda. Okay. So, 2x1 plus lambda basically. Okay. So, substitute it here and get it actually that way. Yeah. Anyway, so any algebra is there, you can, I think it's not that hard to do it actually. Otherwise, there is another way of looking at. Okay, let me correct myself also a little bit here. Okay, you don't do that, let's say, and let's not worry about this algebra either actually. Okay, yeah, let's not forget this comment actually. Okay, so what you can think about is lambda is nothing but that. So what is lambda dot here? Okay, lambda dot, if I just take a differentiation here, is nothing but 2x1 double dot plus x1 dot. Okay, so this is something like I mean, then you can think of using whatever you want to use basically, and then you can try to simplify this actually. Okay, so ultimately the point here is, okay, this now lambda dot, okay, now you can use this one way basically, I mean equation 1a, and lambda dot is nothing but 2x1 plus lambda, and then again lambda is substituted like this and all that actually. So you play around with these three equations, okay, after taking this derivative, and then you will end up with something like this. Okay, so what you are getting here actually ultimately, if you look at these two equations, okay, these two equations now, your 2x1 and 2x1 gets cancelled out. Okay, this 2x1 dot and 2x1 dot gets cancelled out. Okay. Okay. So you are left 2 is getting cancelled out anyway basically. Okay. So you, and then x1 dot is gone basically. Okay. So what you are left out is something like x1 double dot is nothing but 2x1. Okay. Just look at this algebra. I mean, just have to cancel out the terms that are gone and just keep the remaining terms actually. Okay. Okay, so 2x1 double dot will happen to be 4x1, and hence x1 double dot is nothing but 2x1 actually. So this is what we got before algebra, right? I mean, if you look at this equation before, okay, we ended up this equation anyway. X1 double dot is 2x1. Then we carried out the simplification, I mean solution of that and all that way. So this is also similar thing. We ended up with this equation. Okay, so exactly same equation as before. Hence we can proceed the same way. I don't have to do the further algebra actually. Okay. So finally, this expression turns out to be like this. Remember, we have solved this equation that way. C1 C2 is also available as numbers basically. So finally, we have this x1 is that, and x2 is nothing but x1 dot plus x1. So I carry out the algebra that is necessary for this x1 dot, and then add the same expression x1 again basically. Okay. You will end up with something like this. So that is how you get a solution basically. So as I told before, if you consider x2 of t as nothing but u of t, that is a control variable rather, then in the process what you have done is actually we have solved an optimal control problem already basically. Okay. So this is not as simple as that, but we want generality, generalization, and then more powerful things and things like that, but this will also give you some sort of a connection between calculus of variation and optimal control problem actually. That's the motivation of having this example here actually. Okay, so this is what we are gearing up towards that in the next class. But before going to the next class, our main objective in the entire course is to lead towards this optimal control and estimation concept sort of thing. So this is again, I thought I will just put a few words about what the optimal control problem per se. We discussed that before actually anyway. So variety of optimal control problems can be thought about putting it something like this, that our objective is to find an admissible history of control variable now. Okay, that is primarily more important what you have, which will cause these three things. First, it should cause the system governed by this differential equation. Now it is a steady equation. Okay, it's whatever you take the solution u of t and substitute it here and kind of solve this equation, either closed form or numerical, whatever way. Whatever resulting x of t will get is called state trajectory, and that state trajectory should be admissible actually. Okay, it should not violate any constraint on the state actually that way. Okay. So the objective here is to find an admissible time history of the control variable in this segment T naught to Tf, such that it causes the system governed by this differential equation to follow an admissible trajectory. On the way, it should also optimize, that is minimize or maximize a meaningful cost function, and then it should also satisfy this system's boundary condition actually, whatever boundary condition you want to impose. right? Either it can be position constraint or it can be time constraint or whatever you want to do in the final thing, it should satisfy that as well. And on the way it should satisfy this this cost function, okay, which contains partly the path dependent cost and the final boundary condition cost sort of thing. Okay. And discussed about this also, but let me quickly summarize it again. Okay. That this cost function that you are looking at is kind of fairly generic. It can embed various class of problems actually. Okay. First thing we discussed before is how do you talk about minimization of something like operational time. Okay. The time taken from reaching a goal point from starting from a given point. So, that is your minimum time missile guidance, you can think about that problem actually. Okay. So, then in this framework you can think this is 0 and this is 1, okay, then it will lead to that. So, phi is 0 and 1. So, that is nothing but integration of 1 dt is nothing but Tf minus T0, that is what you want to minimize. So, if you take phi equal 0 and L equal to 1, you essentially end up with a minimum time problem sort of thing. Then minimization of the control variable, if you talk about that, then it is U transpose RU, that means R1 times U1 square R plus R2 times U2 square, like that. If R is a diagonal matrix of R1, R2 and all that, then you have this cost function which contains these terms, half of this R1 U1 square plus R2 U2 square and all that, and each of the entries being positive thing, it will lead to something like a positive definite function basically. Okay. So, you want to minimize that, okay. Then you will ultimately end up with minimum control effort. Similarly, if you talk about okay, in other words, if you talk about this, then again still phi is 0 in this thing and L happens to be this function actually. Okay. Similarly, if you have a minimum deviation from the state, minimum deviation of state from a fixed value C with minimum control effort, I talked about that as a kind of a helicopter hovering problem and all that. Then, well, it is x minus C is the error that you want to minimize. So, x minus C transpose Q times x minus C is one term where the error of x with respect to C gets minimized, and then you have U transpose RU where the control gets minimized on the process actually. Okay. So, what you are having? You are still having this phi equal to 0 and L equal to all these things inside, and along with that half is there. Typically, half is also, I mean, this half does not play a major role, but that actually helps us to simplify the algebra later. Okay. Many of these, as you see, these EL equations and all will talk about derivatives. Okay. When you take derivatives or partial derivatives rather, then this half term, because these are quadratic terms, having a half term means half and 2 will go. So, we do not have to carry this number 2 all the way, and it does not really affect the quality of the solution. I mean, the solution where it is supposed to lie, j and half of j will have the solution at the same point, that is more important actually. What you are looking for is the solution of the trajectory itself. Okay. So, that means j or half j minimization is one and the same for us actually. Okay. Then different examples, if you want to minimize the deviation of state from origin with minimum control effort, and you can think of this delta x and delta u, then it is nothing but regulator problem actually. This variable instead of x, it is consider that as delta x being some deviation with respect to some known trajectory sort of thing, and similarly the deviation of control delta u, then this cost function happens to be a regulator problem actually. So, what you are looking for is phi is 0 and L happens to be like that. But what about this kind of a function where you minimize the control effort on the way, but we do not worry about minimization of the states on the way, but you worry about reaching a final goal point C. Okay. So, that means x minus C happens to be at end actually. Okay. So, then you would think of minimizing this kind of a cost function where phi happens to be like this, not 0 anymore, and L happens to be like that actually. Okay. So, these are the class of problems that you talk of, various class of problems that you can embed within this this generic cost function sort of thing. That does not mean you have to confine yourself within this class all the time. You can think about your own cost function as well actually. Okay. And then along with this cost function, we have to have this boundary condition, and as I told before, these boundary conditions happens to be either fixed endpoint, pre-endpoint or variety class and things like that. So, this will embed an optimal control problem, and very quickly in the next class we will see how do we take advantage of this calculus of variation to solve this optimal control problem, where we lead to actually. All that is all in this particular lecture. Thank you.